Okay, so in this example, we're going to look at a half-life of the medicine aspirin as it decays in your bloodstream. Okay, so certain chemicals will decay over time. All your medicines will decay over time in your bloodstream. That's why you have to retake them every 4 to 6 hours or something, depending upon the type of medicine it is. So the half-life of aspirin in your bloodstream is 12 hours. That means whatever you take, according to this problem anyway, whatever you take in 12 hours, you'll have half of it left in your bloodstream. How long will it take for the aspirin to decay to 70% of the original dosage? Okay, so we don't just have to focus on the half-life, the 50%. We can look at other percentages once we develop a formula, and the formula will come from this structure here for an exponential equation. Okay, so the main idea is this: you have a final amount, which I'll call A. You have an initial amount, which I think your textbook is going to call A sub 0. Okay, that's a subscript of 0 there. So A and A sub 0. Then you're going to have some sort of multiplying or decay factor. And the decay factor is going to be 1/2 because we're dealing with a half-life. Okay, so you're constantly cutting the amount in half to get the final amount. And then you're going to have some sort of exponent here. Now I'm going to put an empty box up there because there's some stuff we're going to need. The exponent's not just simple. Remember, even on our financial models, the exponents were a product of a number times time. In this case, it's going to be something similar. Now I just want to point out that this initial value, this A sub 0, is the initial value. Okay, and then the A on the other side is actually the final amount. Okay, so that there is the final amount. Okay, so now let's consider what the exponent needs to be. The exponent needs to be in terms of years. Okay, so I want T is years. No, not years, hours, I'm sorry. That to be hours. That's our unit of time. Okay, so every time I plug in a 12 for T, I want to have a power of 1. Okay, because if I plug in a 12 for T, I want 1 half-life to go by. So I'd have to be multiplying by a half, 1 time. Okay, power of 1. If I had 2 half-lives go by, that's 24 hours. Then I'd want the power to be 2 because I'd have 2 half-lives. Right? So if you think about that, you have T being the years, or the hours. You have the exponent, which I'll put in a box, being the number of half-lives. Okay, I'll call it half-lives there. And so if you have 12 hours, you want 1 half-life. 24 hours would be 2 half-lives. 36 hours would be 3 half-lives, and so on. Well, the only way to make that happen is to take the time and divide it by 12, right? Take the hours, divide by 12, and you'll get those corresponding half-lives. And so that's what the exponent is going to be. It's the time divided by 12. Let me try to write that in here. Time divided by 12. I don't know if you can see that real well. I drew my box probably too small. Alright, so I'll rewrite this so it looks a little nicer. The final amount is the initial value times 1/2 raised to the t over 12. Now, as a general rule, whoa, we can't see that. There it is. A equals a sub 0 times 1/2 to the t over 12. As a general rule, you want the half-life to be the denominator in the exponent. Okay. Then from there, we should be able to make our calculation. We want to determine when the aspirin decays down to 70% of the original dosage. Well, if the original dosage then would be 100%, that's our initial value. The 70% is our final amount. So we'd have 70 in for the A, and the initial value is 100%. Right? That's the original dosage, 100%. Now, I don't know how many milligrams or ounces we're talking about here. It doesn't really matter because we're looking at a percentage. Okay. Then we do 1/2 t over 12. And then if we simply solve this equation for t, we'll have our answer. Okay, to solve for t, I've got to try to peel away all the numbers surrounding the t, starting with the 100. So I'd want to divide both sides by 100. They cancel on the left. And then 70 over 100 is, of course, 7/10, which is 0.7. So I have 0.7 equals 1/2 to the t over 12 power. Now, how do I solve this? Well, the variable is up in the exponent, and whenever a variable is in an exponent, we have to use a logarithm to solve it. So I'm going to apply a logarithm to both sides. I'll just use the natural log. We're going to see probably more natural log in this section than any other logarithm. So I'll apply the natural log to both sides of the equation. Okay, and remember there's an exponent rule, a logarithm rule that allows us to take this power and drop it out front of the logarithm. Okay, that should have been commandment number 9, I believe, on our list of the 10 commandments of logarithms. Alright, so now we have the natural log of 0.7 equals, well, this becomes t over 12 times the natural log of 1/2. Well, in order to get the t by itself, I need to multiply the 12 to both sides, so I'm going to go ahead and do that. I'll change my color here. Multiply by 12. That'll cancel it out on the right. And so I have 12 times the natural log of 0.7 equals t times the natural log of 1/2. If I then divide out the natural log of 1/2 from both sides, that should free up the t value. So now t is equal to 12 times the natural log of 0.7 divided by the natural log of 1/2. Now, if I want to find the actual number of hours, I just take that over to my calculator and type it in. 12 times natural log of 0.7 divide by the natural log of 1/2. And that is approximately 6.2 hours. Okay. So in approximately 6.2 hours, there's a nasty glare there, isn't there? In approximately 6.2 hours, the aspirin will decay to 70% of the original dosage. Now, one thing I do want to point out before I move on from this example is that in your textbook, and I assume in my math lab, they're not going to have you set this up in the same way. They're going to have all of these models in terms of a base of E, just like the compound interest formula. It doesn't really matter to me. I think the conversion, basically the textbook is going to have you do a conversion from the 1/2 to the e. In my opinion, that's unnecessary because we can do the problem just well enough with the 1/2 base. And so we don't really need to do that conversion first. I think it adds to the difficulty of the problem. Although there are some reasons why it's nice to have a uniform base so that we're always using the same base in every problem. But for our purposes, I think we'll be fine just using the 1/2 and not following the exact formula that's in the textbook.